Good afternoon. Thank you very much for coming, everybody. Welcome. Especially want to welcome our friends from all over the place who are joining us online. Today's speaker in the C-STAR lecture series is Dr. Cathy Price. Dr. Price is the director of the Wellcome Trust Center for Neuroimaging in London, and she's a professor of cognitive neuroscience at the Institute for Neurology at University College London. She is has been a pioneer and leader in the field of neuroimaging of language. Many people will know her name from review articles, but she's also very much involved in exactly the kind of research that we're doing here in the C-STAR Center for Aphasia, for the study of aphasia recovery, looking at neural predictors of aphasia recovery, and also looking in general at neural predictors of language delay in children and in adults with language impairment. And she's going to speak about a number of her studies, so I'm going to get off the stage and give it to Dr. Cathy Price.
Well, thank you very much for inviting me. I feel particularly honored, having spent the last 2 days listening to the very, very exciting plans of the C-STAR project, which I know will undoubtedly advance our ability to help those with aphasia. So, the title of my talk is trying to understand functional organization in order to help explain language after stroke. And I've divided the talk into 4 different sections. So first of all, I'm going to actually provide you with evidence that speech and language abilities do actually change years after stroke. I'm then going to discuss what the neural mechanisms for this might be and why it is that there might be more neural adaptation in some patients than others, and finally then come back to think about how we might use this information in the future to predict how well a given patient will recover. Before I go on to address the first question, I want to tell you about the data that I'm using, because like the C-STAR project, I've been developing a database of people who have had strokes, most of which have had aphasia as well. This is the PLORAS study, which stands for Predicting Language Outcome and Recovery After Stroke, and we collect from every subject a structural MRI, a lot of demographic information, some behavioural scores, not nearly as many as you're doing here, and for a select few we do functional MRI as well. And I personally don't do any therapy studies, but I do refer patients for therapy studies, and that's with Alex Leff and Jenny Crillian. So at the moment we have just over 1,000 participants on the database, and the calculation is that 801 of them have aphasic, apraxic, alexic, or agraphic symptoms at test when we see them, and then we have another 112 who are not aphasic at test, but they were previously aphasic, but have recovered by the time they've seen us. We have a few that were never aphasic, and then we have a few others that are not currently aphasic, but we don't actually have any information on them. So that's just a sort of outline of what we had. And this data is here for sharing as well, so if any of you want extra data, particularly, for example, if you were interested in particular lesion sites, then we can provide the data that we've got for you to test some of your predictions. Now, one of the things that might be different from the data that we're collecting compared to the data you're collecting is the time post-stroke that we see the patients. So we do have a number in the first 3 months, about 40 or 50 in the first 3 months, and then at 3-monthly intervals. But as you can see, this is a plot of the number of patients in the database versus the year with which they were tested. So although most of the patients have been tested in the first year, and we'll try and follow them up as much as we can over their years, you can see that we've collected data right the way up to more than 25 years post-stroke. So these are people that have been brought in from the community who've had strokes, and then we look to see how they've recovered, and we try to map their recovery to their brain structure. So it's different because we're looking a very long way away. So my first question then is, do speech and language abilities really change years after stroke? And what's our evidence for that? Well, firstly, if we take all the patients and we group them according to the initial severity that they presented with at 1 week. Now this is self-rated, so it's how they feel about it. It's not us observing or recording the data. But we asked them to rate how severe their aphasia was, or their ability to speak was, at 1 week after the stroke, a month after the stroke, and then a year after the stroke. And what I've done here is to split the patients according to how they rated themselves in the first week. And then what you can see is that if they were severely impaired, most of them have said that they are improving over the first year. So what we have here is longitudinal data indicating that poor initial severity is associated with poorer speech at 1 year. That's a well-known finding, so initial severity is correlated with outcome at a year. And of course, there's more scope for improvement in those who are most severe. Now, of course, we could say, well, that's how people feel about their strokes. It's a subjective measure. But we can also go on to start looking at, if we just look at that bottom line there in red, those that were most severe, and then we divide them according to their lesion site, we can see here that there are different rates of recovery that are being related to their lesion site. So this starts to sort of give us, to suggest that some of the variance that we're seeing here is actually real, because it can be accounted for by lesion site. But again, this is subjective data. This is observed data in 118 patients who have very small left hemisphere lesions. So these were, the size of the lesions were between 1 and 4% of the left hemisphere. So that, I mean, they're still relatively large insofar as they can be a centimetre cubed. Look at this data here. What you see is that in the first 4 years, we have a lot of patients who are in the normal range, and we have a lot of patients who are in the aphasic range. So we've got a lot of variability in how these small strokes are affecting speech scores. And this is, the test is a picture description task. But if we look after 4 years, what we see is that most of the patients that we've tested here are all in the normal range. So, and if we count that up, in the first 4 years, we have 66 out of 86 of the patients were in the normal range. That's 76%. And if we look at those after 4 years, we've got 32 patients, and 29 of them were in the normal range. So 91% of these patients were in the normal range. Again, this is cross-sectional data, so we're not actually demonstrating here that the patients are improving, but the cross-sectional data suggests that there's far more variability for these small lesions in the first 4 years than there is later, and that most of these patients have recovered from their small lesions. And now I'm going to just give you an example of what sort of patients are contributing to that. So one example are lesions to the left putamen here. And if we go into the database and we search for patients that have got small lesions to the left putamen, I've plotted them out here. If you can see them, they're just little grey spots, and these big circles here is just the mean at each time. So when we look at the cross-sectional recovery of patients with these lesion sites, it looks like they're again improving in the first few years, and then all of them are above later. So that suggests that perhaps we might be able to, in future, predict that patients who are aphasic after left putamen damage are likely to be back in the normal range. And we're obviously following these patients up to see whether these predictions can be observed longitudinally as well as cross-sectionally. And this is a recent finding that my collaborator Tom Hope has produced. So it's currently in revision. And what this is patients who've got large lesions and who've been tested longitudinally at more than 2 or more time points, months post-stroke. This is in months rather than years, but you can see this is all the way up to, yeah, well, way over 10 years. 20 years here. So this is their object naming score, and each of the scores per patient have been linked together. And what you can see in blue are patient scores that are increasing over time, and what you see in red are patient scores that are decreasing over time. And most of them who are impaired are still impaired. They've got massive, great big lesions, and most of them that are in the normal range are still in the normal range. And if we average over all the first and the second incidences, what we see here is absolutely no difference in the mean score. So what that would be consistent with is that, well, in this chronic phase and many years post-stroke, these patients aren't really changing. This is all just measurement noise. But we can test that. Is this real or is it noise? And we can test it by looking to see whether there are any areas of the brain, of the intact brain, and I'm just going to show you what happens in the right hemisphere. Are there any areas in the brain where, when a patient is improving, their brain structure increases, and when they're deteriorating, their brain structure is declining? So we can do a voxel-based morphometry analysis, very much like many of the studies that have been conducted in healthy controls. So the London taxi drivers, looking at the hippocampus changing. We've done a lot of work with looking at bilingualism. When healthy people learn a new language, their brain structure changes. And we've also looked at teenagers and looking at their IQ changing in the teenage years, and showing that IQ changes also correlate with brain structure. And when we look to see where that effect is, or even to test the validity of this data, what we see is that there's a region in the right middle temporal gyrus where the rate of change in score is significantly correlated with the rate of change in the brain structure. Now that cannot be explained by measurement error. So something real is going on here where brain structure is reflecting something that is happening long term. We can also do an outward sample cross-validation of this data, so using a leave one out analysis to see whether or not the change that the structure in the brain region that is changing can be used to predict the scores in new patients. So this is the observed change in score, and this is what would be predicted for each of these subjects based on all other subjects. And what we see here is a very tight correlation between the two, showing that this area is highly predictive of what's happening with these scores. So despite the fact that this would normally be considered as measurement noise, these results are showing that it can't purely be measurement noise. Something really is happening to the patients. They're either improving or they're declining, or some of them are staying constant. So that's the first part of the talk, which is just showing you evidence that there is some change. And the second part of the talk is to move on and talk about what the neural mechanisms might be that are supporting this and how is it occurring. If we come back to this result, we can start to ask, well, what is this brain region doing in object naming in those that are either recovering or declining? And the one way that we can investigate that is to use a functional imaging experiment in healthy participants and say, is this area here actually activated in object naming in healthy controls? And what aspect of object naming might it be involved in? And what we found was that this area here is, just doing a region of interest analysis, is activated with a very high Z-score for object naming more than semantic decisions on exactly the same stimuli. So we've controlled out all the perceptual processing, and so it's involved in some part of producing the name of the object. So that, again, suggests that these changes that are taking place are taking place in a region of the brain that is normally involved in object naming. It's not taking place in a completely new brain region or anything that's unrelated. It's not general plasticity. It's focused on a part of the brain that can serve some role in object naming. Now what I'm going to do is to show you an example of how functional imaging doesn't work when we're trying to link functional imaging data and lesion data. And this is an example of an activation from a semantic matching task. So this is, again, in normal participants. And what I'm going to show you is some activation in normal participants, and then what happens when you damage the region. So first of all, just to familiarize you with the normal system, so the activation task is like the pyramids and palm trees task. There's a target item here, a piano, and the patient has to decide which of the items below it's most semantically related to. So you're supposed to match the piano and the harp here, and you press the right button to indicate that this is your target response. And we have a baseline task, but we also compare it to a baseline of rest as well. But the baseline task is just a perceptual matching task where they decide if the item at the top is most similar to the one on the left or the one on the right. Now, when I've presented this before, everybody can argue about what are the processing differences between these two tasks. Actually, it's really not important here, so we're not trying to understand exactly what these brain regions do. What we're trying to do is to look at what areas of the brain are activated and how consistently are they activated. So what we see in healthy controls, if they do this task, is that there's a very significant and consistent activation that occurs in the left frontal cortex. And there's also areas in the left posterior inferior temporal lobe and also the left posterior middle temporal gyrus. So these are areas that are consistently and highly significantly activated in healthy individuals. So the next question then is, do these activations from fMRI predict how a patient is going to respond if they have damage to these regions? So now what we're asking is, does damage to these regions result in semantic matching difficulties? In this slide here, the yellow areas that you see here are all exactly the same on every single brain. They are the regions normally activated by semantic matching. And what I've done is to superimpose this set of regions again and again on the brains of different patients who've got lesions to these areas. So in the top row here, the patients have got very large left frontal lesions that damage the frontal and the temporal cortex. Here we've got patients that have got damage to the frontal cortex, but they've spared the temporal regions here. And these patients here have got damage to temporal regions, but have spared the frontal cortex. And these ones had damage to the connections between the the temporal and frontal regions. So the question is, what happens then to these patients? And the answer is that the speed and accuracy of their semantic matching was within normal range for all of these patients. So in other words, we have a set of areas from fMRI that are being consistently activated in the healthy brain. You remove them, and these patients can still perform the task extremely efficiently. So comparing fMRI in normals and lesion effects in patients provides evidence that damage to areas that are normally active for the task don't necessarily impair performance on that task. So sometimes they do, and sometimes they don't. And what we need to do is to understand why they don't and how it is that patients are able to recover. One way to investigate how a patient's recovering is to conduct functional imaging experiments of the patient and performing the task that they're able to do, so performing exactly the same semantic matching task in exactly the same way that the healthy patients do, and say, how are you doing it? Which parts of your brain are activated, and does that indicate what the compensatory pathways might be? And here's an example of 6 activation patterns from the different patients. So they're doing, this is them making correct semantic decisions. And what we see here is that their good task performance is associated with consistent activation in the posterior inferior temporal lobe. So although some of them had damage to the frontal and the temporal regions, it turns out that in this sample of patients who were very good at performing this task, none of them had damage to the posterior inferior temporal cortex, and all of them were activating this. So that's one consistent result that we can have something to get a handle on. On the other hand, probably what you're most struck with is, oh my goodness, they're all doing something different. And that is what we see, and that there is enormous inter-subject variability in how people respond when you start doing fMRI experiments on them performing the task with large lesions. And I'm not going to solve the problem or to tell you how we have resolved it, because we haven't yet, so we're still working on trying to find patterns of activation across patients. But what I will do now is to move to theoretically talking about how this might happen. And I'm going to talk to you about a framework for understanding functional reorganization, which I refer to as so it is an unfortunate name because degeneracy implies that the brain is degenerating, but the word degeneracy actually comes from biology and mathematics, but in mathematics it means that there are 2 different ways that you can solve the same problem. And in biology, this is a Wikipedia entry. Degeneracy is the ability of elements that are structurally different to perform the same function or yield the same output. And the thing about degeneracy is that it is evident throughout biological and physical systems, from genetic codes to body functions to brain functions. And for people who are psychologists, I think it's probably best sort of indicated in different strategies for doing the same thing. It doesn't mean that 2 different brain regions have exactly the same function. It means that different sets of brain regions are able to reach the same output. So I'm going to hopefully entertain you with some videos. And what these videos do is to try and illustrate what I mean by degeneracy, using examples of degeneracy in body movements, and then coming back and to use analogies to try and understand structure-function mapping in the brain. So, in the examples that I'm going to give you, I'm going to distinguish between different types of degeneracy. So we can have degeneracy which is using typical structures. So this is typical in healthy, normal controls. The patients are using systems that are already there. Or they might be using a subset of the typical structures that are sufficient to perform the task, and they haven't needed to do all of them. or they may be using atypical structures that are not used in healthy controls. And then I'm going to also just show you some intersubject variability and support mechanisms for doing a task, where there might be one set of things that you need to do a task, but there are other things that we do in order to make the task more efficient. So here's an example of a typical strategy, and it's one just simply of writing, because it's one that we're all familiar with. So with writing, we can use alternative strategies to complete the same task. We can write with the left hand, or we could write with the right hand, and our proficiency in doing so depends on our handedness, our potential, and the practice that we've had. And these are the things I'm going to emphasize: potential and practice. So I asked my daughter to write laugh and smile with her right hand, and here's her schoolgirl writing. And then I asked her, can you do the same thing with your left hand? And she went, no. So after a lot of bribing and discussing the matter, I suggested that she really would be able to do it, but she truly had never been asked to even attempt to write with her left hand, because she's so dominant with her right hand. So this is her first ever attempt to write with her left hand, and you can read what she's written: laugh and smile, laugh and smile. So her left hand was able to pick up that function, even though her left hand had never done that before. I then asked her, can you do it with your toes? And she said no. And I'm sorry, I don't even have an example, and no amount of bribing would get her to write with her toes. So she wasn't able to do it with her toes, but I know people can do it with their toes, because I have Christmas cards that are sent to me that are painted by people who do it with their toes. So there's a charity for these people to sell. They sell their Christmas cards. So my point here that I want to make is, with this familiar example, is that it is possible to do the same task in different ways, but there are a limited number of viable options. And there's not only a limited number of viable options, but they become less and less proficient. So my daughter's best hand, then with her left hand, then with her toes. Well, not very good at her toes, but there are some parts of your body that can never take over that function. So it's not the case that either your body or your brain can just magically take on a function that it had no capability of doing before. So I've talked about typical structures, and I'm now going to talk about using a subset of the typical structures. And here I've got a video that I love. It's a girl who's playing the piano, and she's got no fingers on her right hand. It's one of a series of China's Got Talent, and they've truly got talent. So listen to this. Isn't that wonderful? So now this one is a stroke patient who's lost the use of his left side, and he's playing the piano with his right hand. A lot of effort has gone into this. Don't need to hear it again, but the point is that with a lot of learning, he can learn to use his right hand doing a task that he'd normally do with both his hands. And then I'm going to give you another example of somebody from China's Got Talent using atypical structures to play the piano. And this is somebody who doesn't have any arms, and he's playing the piano with his toes. One more time. Great violins in the background. And finally, I'm going to give you an example that doesn't come from piano playing, it comes from people running, just to show you intersubject variability in support mechanisms. And this is with running. So it's clear what we need for run. We need to have our legs in order to run. We need to have our arms to run. But we also need to balance ourselves too. So it's just an example of how support mechanisms allow the basic structures to work most efficiently. And it's quite amusing and I enjoy it. So here we are. So this is the runners. Typical structures are used in different ways to balance themselves. So that's all sufficient. They're all running very nicely, but all in different ways. So in summary, from that diversion from the problem with fMRI, there are different ways of achieving the same output. And what I'm arguing here is that the proficiency of each system depends on its potential to actually perform the task and also practice, and long-term practice years after stroke. I think that degeneracy provides a useful framework for modeling inter-subject variability as differences in preferences for different strategies. And the preferences will depend on their proficiency, which depends on the potential, practice, and plasticity. Lots of P's. And understanding functional reorganization, which is effectively learning a new strategy, by degeneracy allows us to place limits on the number of efficient options that are available. And therefore, it helps us to think about how we might predict the effect of brain damage, because if we could unravel the systems with the potential to support the task, then we can predict recovery on the availability of potential systems. Okay, back to the talk. So the second part of the talk then is the neural mechanisms. We're still in the second part of the talk, so I'm just going to bring it back to the brain mechanisms and then talk about how this might work. So here we're talking about, are there alternative neural pathways for the same task? And so here's just an example of a task that might have two routes. We're going to, I'm going to go on to give you a more realistic example. So this is just a theoretical example. There's two different routes, and the argument would be that if both of these routes are each able to support the same task, then recovery from damage to one pathway should occur if the other pathway is available to compensate. But there'll be no recovery if you lost both pathways. So just to illustrate that, is damage to one pathway here. The patient should be able to recover here, and he's damage to two pathways here, and the patient then doesn't have a route in order to recover. And here's some real data. So this is showing groups of patients that either have damage to the left inferior longitudinal fasciculus and coming right the way up here, right the way through the white matter up into the motor cortex. And this is another group of patients who've got damage to the motor cortex that also runs right deep into the white matter here. And these are their scores when on a spoken picture description test. And the red, this is normal here, the normal cutoff, 60. And the red scores here belong to this group of patients here. As you can see, they're below the normal cutoff. These yellow scores here, it's just slightly lower than the red ones, belong to this group of patients here. And these two groups of patients here have got damage to both of these systems. And there's two different groups here because one of them has been matched to lesion size, and this is all the rest of them. So lesion size is actually having very little effect, and this is the floor effect here. So that they are still able to name some, but you can see that their performance is much worse when there's damage to both of these systems than when there's damage to one of these systems, even when lesion size is controlled. So we can't necessarily say whether or not that each of these systems can compensate for one another, because clearly, even when one system was intact, the patients are still impaired. But what this shows here is an additive effect of damage to both systems on the scores. So it still shows an interaction in the effect of two different lesion sites. So here I'm just talking about grouping patients together as if they're all the same. And the next part of the talk, I'm going to talk about why there might be more neural adaptation in some patients than others. I'm going to come back to talking about these patients who've got left putamen damage, which I showed you earlier, and this is the same plot I showed you here. So this is years post-stroke, this is their speech score, and this is them recovering, well, not recovering, this is cross-sectional data showing that those that are impaired are early post-stroke, and those that we've tested later post-stroke seem to be in the normal range. And how we can summarize that data is to say that following posterior putamen damage, either patients have a temporary speech deficit, so this is hypothetical because this is cross-sectional data, but this is the hypothesis, that either patients have a temporary speech deficit or they have no speech deficit. So those are the two options. This data doesn't suggest that anybody's having long-term speech deficits. So we have these two options here. And then what we can do is go back to fMRI and see if we can understand that in healthy controls and start looking at the role of the putamen in healthy speech production. So this is a paper by my colleague Mohammed Seghi. Actually, it's two papers. And this is healthy controls, and it's looking at how activity in the ventral occipital temporal cortex during reading connects to motor regions. And we modeled it so either it went via the putamen or it went via another route, which we later started to work out involved parts of the premotor cortex. So we've got in the controls, we're testing, there's two different routes, and here's all the different subjects, the healthy subjects. And what we can do is estimate the strength of the connectivity between these different regions and show that some subjects prefer the pathway that goes via the putamen, so the strength of their connectivity is stronger for the putamen than for the other pathway. And this group of subjects, though, it was the reverse. They had stronger evidence that they were using the other pathway than the putamen pathway. And then there was a group in the middle who involved both equally. So no difference here doesn't mean they weren't using either. It means there's no difference between the two. And what that allows us to do then is to start producing hypotheses as to what could happen in patients. So what we're seeing here is that the normal preference is to either use the putamen pathway or to use another pathway. And then we would predict that those healthy participants that normally use the putamen, they're the ones who are going to be affected by putamen damage. So they're going to have an effect on their speech production when they're trying to read. But because there's another pathway that's available, we then expect these ones to recover. And that would explain why you get a temporary effect of speech production after putamen damage. And equally, it also explains why there's another group of patients who don't show any effect, and we'd predict that what happened normally was that these patients didn't rely on the putamen, and therefore they didn't have much functional reorganization. There was just a very minimal effect on their speech production. So together, the fMRI data and the lesion data helped to create a theory as to what was causing the inconsistency in the response to damage to the left putamen. Now, I just presented you some data on reading without going into, well, what are the cognitive components, what's the difference strategically in terms of the functional components that are being used. But what we do a lot about cognitive models of reading, and there are multiple different versions of them, and I'm going to just show you the most schematically simple one, which is just the dual root, or not, it is a dual root, but it's not the dual root model, showing the different ways that you can read visual words. So the idea is that when you're reading visual words, you access the orthography, and the orthography can be mapped onto the phonology, and in this case it's the speech output plans, and it can either be mapped directly, for example, when you've got a word that has got regular spellings, like ship, or a non-word like shup, or if there's not a regular mapping between the orthography to the phonology, then it can be mapped by recognizing the word and going through semantics. And that would be for something with an irregular spelling like yacht, but ship could be read by either route. So here the hypothesis would be that if you had damage to this pathway here, you would have more difficulty with non-words than you would with words with exception spellings, which can still be read by semantics. In contrast, if you have damage to the semantic roots, you'd expect the patient to be better with non-word reading than with exception word reading. And mapping that with functional imaging, and again, this is very simplistic work which was done with my colleague Andrea McKelly in 2005. We just map on what some of these systems are. We can, in gross terms, we've got orthography in red here, the semantic system in yellow, and speech output system in green here. The details aren't useful, but in this particular work, what I want to show you is if we put all of these systems together, what we showed was that when healthy controls are reading non-words and exception words, there are two different pathways linking the ventral occipital temporal cortex and two different parts of the ventral occipital temporal cortex, a posterior part, which is linking up to the premotor cortex, that was more strongly integrated or for non-words than for exception words, and the semantic route linking the anterior part of the ventral occipital cortex to the ventral part of the inferior frontal cortex that was more strongly connected for words with exceptional spellings than non-words. So the reason I'm introducing this is to start to introduce just how very complex all these different pathways can be. So here's an example of two different pathways for reading that are consistent with cognitive models. But before that, I introduced you to another pathway using the putamen, which is not consistent with a prior cognitive model. And then I want to go on to tell you that in subsequent work, we've identified further reading pathways. So let me, I'm going to show you this, and so I'm going to get to its most complex part, and then I shall stop. So in cognitive models and functional anatomical descriptions, or classic ones of how the reading system might work, this ventral occipital temporal region here is known to be critical for reading, and damage to this region is classically associated with pure alexia. Personally, I don't believe in pure alexia because I've never seen a patient with pure alexia who doesn't also have an object naming difficulty. If you push them hard, they will start to, their object naming will also start to break down. But the point I want to make in the example I'm going to give you is that when you have damage to this region, even in patients who've got reading difficulties, what typically happens is that they start to recover by, first of all, starting to be able to read very short three-letter words, and very often starting to build up to longer words by developing letter-by-letter reading strategies. So they start over the years to learn. And we scanned a patient who had a very large lesion in the left ventral occipital cortex. She was unable to read for a long time, and then she started to learn to read again. She started to get quite good at reading short words, and she started to work out long words. And it took a long time. It took years. So this is long-term functional reorganization. And then the work I'm going to show you is again with my colleague Mohammed Seguier. It was published in 2012. So we scanned this patient doing what she's good at, which is reading short words, and she read the short words in the scanner. And this is what we found. So here's the patient's brain with a big lesion here in the ventral occipital temporal cortex. And these white regions here are the pathways that I've just shown you for non-word reading and exception reading. So she's damaged both of those. And what we found was she didn't activate this area, not surprisingly. She's got a huge lesion in this region. What she did was she showed increased activation in a more ventral occipital region, increased activation in the left superior temporal sulcus, and then she had strong connections between this region and areas that were going to initiate her speech. So in summary, the results showed that damage to the left ventral occipital temporal cortex caused reduced use of the ventral occipital temporal pathway, but increased activation in another pathway that was being linked by the linked to the ventral occipital cortex. So this doesn't fit with any of the models, either the functional anatomical models or the cognitive models. So we start to create something, or we need to put a direct link between occipital regions and into the superior temporal gyrus and sulcus. And then we go back to the healthy controls and we say, is it the case that some healthy controls are also using that pathway? And we find, yes, it is. So most of them will use both pathways. They'll link the inferior occipital cortex both to these two regions independently, and some healthy controls will use this pathway, like the patient did more, and some healthy controls will use this pathway more, like one that she couldn't use. So we start to see that these multiple pathways are actually there in the healthy controls. And then in further work, we've been trying to divide up what's happening in the superior and inferior parts of this ventral occipital temporal cortex, and we're starting to unravel that there are even more pathways coming in here. So I'm getting very complex again, but the complexity of these models, if we can characterize it, is what's going to tell us how these patients are recovering. So understanding this sort of information is very important for explaining how patients are able to recover. As if you're not had enough challenges, here there's another thing that, another implication of the results that I've been giving you about people performing tasks in a different way, and that's the implication of degeneracy for interpreting fMRI activation studies. Because if every time we conduct an fMRI activation study, we pool together subjects that use different strategies, then what we're going to get is a complete morphing. We've got one group of patients who are activating doing one thing, or another that are doing something different, but what we actually measure is, so there's one group, two groups, what we actually measure is a mixture of the two. So we've got a mixture of the morphing of two different images together, because we're averaging it across different subjects. And then we have false negatives, where features vary between groups, so you don't get any significant effects. And we've got false positives, when there are combinations of features that create new features. So this is something that we have to be very careful of when we're interpreting our functional activation studies. What we need to do is be able to take the average activation and pass it into different groups of what are the most likely pathways. And this is the type of work that we've been doing, for example, with the putamen, trying to see which patients, which healthy controls are using the putamen and which aren't using the putamen. So finally, how could these results influence or affect or help how we might predict how well a patient will recover? Well, actually, it's probably not been at all helpful. What it does is it actually raises a lot of challenges. But the first conclusion, and it's one that I've heard discussed in the last couple of days here as well, is we really need to move away from overly simplistic models. They are so appealing. This is the 19th century neurological model. It is so appealing to think about reading as a visual input up to the visual word form, area. This is the old version, not the new version. And then into Wernicke's area for a bit of phonology, you're accessing the sounds, the images of auditory images of words, and then into Broca's area, and then up through the motor cortex. That is so easy and simple for everybody to understand. It still goes into all the textbooks. But of course, the alternative is, and of course this is completely unrealistic, but the alternative is that we're going to get something which is incredibly complex, because we've got to start looking at physiologically plausible and predictive models of cognition, which will involve unveiling all the possible neural pathways that could support a task and reconsidering what the underlying computational functions of these different regions and networks are. So that's something I think way into the future, but it's quite an addictive thing to keep studying it. But meanwhile, and again this is consistent with the C-STAR project, is not only understanding how recovery is occurring, but also to use data-driven approaches. And this is an example of an approach that we've been using. So you take a new patient with an MRI and some demographic information. We extract out the lesion. This is much simpler than you're doing it, because you've got many more types of imaging and types of predictors which are going to massively improve your ability to predict relative to this. But I'm just giving you a simple example of just having an MRI. We extract a 3D lesion image. We then search through our database for other patients who've got similar lesion features that we define in multiple experiments, and we add in the non-lesion features as well. We then generate a prediction, and then we look to see what the database tells us about all the other patients that we've tested. And possible outcomes could be that the patient is improving over time. So here's an example of a prediction where the width here of the bar tells you how much variance there is with other patients. So this is a fairly confident prediction that the patient's going to improve. Here's an example of a prediction where we're predicting the patient's not going to change over years. Here's an example of a prediction where we're expecting decline. And these are all real predictions that have come out of the predictive function that we're using. And then, of course, a very large number of functions might come out looking like this, where the data on the database indicates that some patients are going up and some patients are going down and some patients aren't changing. So we look for a mean, but there's so much variance in here that it's not very meaningful. But what this does indicate is that the lesions where we see this interpatient variability, these are the ones that motivate us to try and understand this group of patients more, where we're not able to predict what's going to happen to them. And I'm going to just finish by showing you the three lesion sites that we found that are most predictive of who's going to have normal speech. And if I just show you this video, there's just three regions here, so it's very overly simplistic. For example, it doesn't have the putamen in it or other regions that we've looked at. But there are three regions that are informative in a new way. So we have this red premotor region, which has been identified in many studies, including ones that have done here. associated with motor speech function. We've got the left inferior longitudinal fasciculus here, and we've got a temporoparietal area here. So whilst we can make consistent predictions for the red and the yellow regions, the temporoparietal region in green is included purely because it has such an inconsistent effect on speech production. The reasons I've included it, let me just that again. Oops. The reason I've included it is because when we include it and then we look at all the patients on the database who've saved these regions, we find that 90% of them have got their ability to produce sentences back into the normal range in 1 year. So it's been important to identify as many lesion sites as possible in order to make predictions as to who we think is going to be back in the normal range. And that's my concluding slide. And I'd just like to acknowledge the many people and funding sources that have enabled this work. So we're funded by the Wellcome Trust. We did have funding from the James McDonald Foundation. We've currently got funding from the Stroke Association and the Medical Research Council. Got different institutes supporting the research, and we divide into 3 teams, a little bit like you have here. We have a data collection team, so these are mainly speech and language pathologists. We've got a data management team, so these are people that are looking after the data, and then these are the people who are analysing the data. Alex Leff and Jenny Crinion are both doing intervention studies on subsets of the patients. So thank you very much.
Start with questions in the room. If we have questions from online, they'll be coming up on the chat box, and I'll just read them.
So I was interested with the work of Thomas Hope that shows that some of your people get better over time longitudinally, some get worse, and you seem to suggest that it's this right hemisphere area that seems to predict something. Is it that people who get worse are sort of diminishing in that region and that's atrophy, or is it actually increases in what you're measuring?
Well, Thomas looked into this very carefully and shown that it's both increasing